We have this indoor and outdoor PCB setup, and as soon as power is supplied to the system, it displays an EE error. Right now, I've connected the indoor and outdoor units electrically, and the purpose of showing this is to confirm that all connections are properly made. Despite everything being set up correctly, the error still appears. So we now need to troubleshoot and find the cause of this error. But before we begin the diagnosis, let me show you the error in real time. As soon as I supply electricity to the system, it displays a temperature reading of 16 degrees. Now we have to wait a little because the outdoor unit won't turn on until the indoor unit finishes its switching process. Even though it's quite hot today with a room temperature of around 35 degrees Celsius, the relay is taking a bit of time to activate. We'll wait for the relay to switch. Now the relay has clicked and the system has turned on, but immediately the EE error has appeared on the display. Let me turn off the light to show it clearly. Yes, the EE error is currently being displayed. Now we need to determine whether this EE error is coming from the indoor unit or the outdoor unit. Although it's generally confirmed that this error is related to the outdoor unit, the system only shows EE, which simply means an EPROM fault. When the EPROM becomes faulty, this error appears. However, the company hasn't specified whether this EPROM fault originates from the indoor or outdoor unit. The issue is that if we attempt to repair the outdoor unit, and the actual fault turns out to be in the indoor unit, it becomes a frustrating and time-consuming problem. That's why, to clearly identify the source of the error, we'll use a simple and practical method that will help us confirm whether the issue is genuinely with the outdoor unit. Let me now show you exactly how we're going to do that. Now, here's what we're going to do. First, we'll turn off the power supply. If you look here, you'll see the wiring. This includes the line, neutral, and signal wires. What we'll do next is disconnect the signal wire. After that, we'll turn the power back on. As soon as I power the system, you can see that the display shows a temperature of 16 degrees. Now, this part is important. We'll keep monitoring the system closely because, with the signal wire removed, the error should not appear. Also, pay attention to the moment when the indoor unit tries to send power or a signal to the outdoor unit. This is typically when the error pops up if it's going to happen. Since the microcontroller takes a little time to initialize, we'll need to wait patiently and observe. Stay alert and keep watching whether any error appears after the indoor unit sends power to the outdoor. If the system runs without any error during this phase, it's a strong indicator that the fault lies in the outdoor unit. While I'm already fairly confident that the issue is in the outdoor PCB, this method is especially useful for beginners. It's a simple way to verify the fault without having to guess. This helps them learn and troubleshoot logically instead of replacing parts blindly. Now look, both indicator lights, LEDs, have turned on. One of them is blinking while the other remains continuously lit. The display is still showing 16 degrees, and we now need to wait for a bit. This waiting period is important, especially when trying to pinpoint whether the fault lies in the indoor or outdoor unit. If you're ever in a situation where you need to identify the fault between the two units, now based on this setup, if the system still shows the EE error, then it clearly indicates that the fault is in the indoor unit. If a different error code appears, then it likely means the fault lies in the outdoor unit. Let's wait a little longer to observe the system's behavior and see which error shows up. Now, as you can see, the system has displayed the E0 error, which in this unit indicates a serial communication error. This confirms that the issue is indeed with the outdoor unit, not the indoor one. So now, let's focus on the EPROM located on the outdoor PCB and try to understand the different scenarios that could lead to this error. If we examine the outdoor PCB, we can see the EPROM clearly positioned there. There are typically 2 or 3 possible reasons for faults related to the EPROM, and any one of them could be responsible for triggering this error. One common possibility is related to the operating voltage. The EPROM operates on either 5 volts or 3.3 volts, depending on the system design. It works in coordination with the microcontroller, which supplies these voltages. Another possible reason for this issue is corruption in the EPROM's internal data or flash memory. If the firmware or software stored inside the EPROM becomes corrupted for any reason, it can also lead to communication errors like E0. The third cause could be a physical fault inside the EPROM IC itself. If the internal circuitry of the EPROM becomes damaged, then it won't function properly. The fourth possible reason is a failure in data communication between the EPROM and the microcontroller. Even if the supply voltage is fine and there's no obvious physical damage, if the data, SDA, or clock, SCL, lines stop functioning, as a result, the microcontroller cannot access the data, and it will display an E0 or EE error on the screen. There are 2 or 3 effective methods to fix this kind of issue, and based on my experience, the most common cause is data corruption inside the EPROM. When this happens, the system starts giving communication errors. One way to fix it is to reprogram the EPROM with fresh software. either by removing the chip from the board or, if your system allows it, by flashing it in circuit. In many cases, this alone resolves the problem. However, I've also observed that when data gets corrupted, the physical structure of the EPROM IC may also be compromised. That's why the best and most reliable approach is to remove the EPROM from the board entirely. If you have the correct firmware or software file, write it into a brand new EPROM chip, and then install that new chip back onto the board. This is the most effective and long-term solution, especially when you're confident that data corruption is the root cause. So, that's exactly what I'm going to do here. Even though testing is very important in any repair process, in this particular case, I'll skip advanced diagnostics because I'm certain, based on experience, that it's a data issue. Plus, I need to return this unit to the customer quickly. So without further delay, I'll remove the faulty EPROM and install a freshly programmed one to resolve the problem. Now we're going to remove the EPROM from the board using the traditional method. First, we'll heat up its solder points slightly. By applying a bit of fresh solder to the pins, we soften the existing joints. This helps loosen the legs of the IC, making it easier to remove. After slightly heating the pins, we begin the extraction process. The chip is almost ready to come out. I'll now flip the board and gently push the IC upward to check if it's loosening, but it's still quite tight. So, I'll carefully insert a small screwdriver underneath and apply slight pressure while continuing to heat the pins from the backside. As you can see, one side of the EPROM has now been lifted. I'll do the same for the other side, slowly heating and lifting it. Next, I'll insert a tweezer under the IC, flip the board over, and firmly grip the EPROM with the tweezers. I've noticed one of the through holes is blocked, so I'll reheat that point. Now, to complete the removal cleanly, I'll reapply solder to the pins where I removed it earlier. Doing this helps keep the joints soft and ensures the IC can be lifted without damaging the PCB pads. As a result, the EPROM chip has now been successfully removed. Now, we've identified the EPROM IC as 24C08A, so we'll replace it with a new chip of the exact same model. I've already explained the full method for programming this IC in my other videos, so you can refer to those for detailed instructions. For now, I'll continue the process quickly to save time. I've taken the EPROM programmer and inserted the new 24C08AIC into the socket. It's now properly attached. Next, I'm going to run the programming software from my computer. I will directly execute the exe file to launch it. The program has successfully opened, and it has detected the serial number of the programmer. Now, I'll use the Smart Identify feature. Once selected, it automatically detects the chip's capacity and details. Before writing any data, I want to check if this new EPROM already contains any program. So I will click the Read button, and as you can see, there is already some data present. I'll cancel that and proceed to erase the chip. Now it has been completely erased. Next, I run a verify operation to ensure everything is clear and ready. The verification confirms that the EPROM is now clean and ready for programming. Now I'll read the EPROM again to confirm its status, and as you can see, it shows that the chip is completely empty. I'll cancel this operation. Looking at the buffer section in the software, it's also blank, confirming that the EPROM is clean and ready. Next, I'll open the program file that I had saved earlier. It's named Kenwood Outdoor Unit LT1558, and it's located in the same folder. As soon as I select and open the file, the entire buffer zone fills up from top to bottom with the program data, which means the firmware has successfully loaded into the software buffer. Now, I'll proceed to write this data into the EPROM. Once the write operation begins, you can see the data is being written to the chip. This confirms that the EPROM is now fully programmed and ready to use. With the flashing complete, I'll now remove the IC from the programmer socket carefully. Now we need to clear the PCB holes where the EPROM was previously installed, because without clearing these holes, we won't be able to fit the new chip properly. Once the holes are clean, I'll place the new EPROM into position. To keep the chip steady, I'll slightly bend one of the legs to hold it in place. This will prevent it from falling out during soldering. After securing the chip, I'll proceed to solder all the pins carefully. With the EPROM now soldered onto the PCB, it's time for the final testing. I've already prepared everything, wiring, connections, and setup, so I'll power on the system. As soon as I switch it on, the display shows 16 degrees Celsius, and now we need to monitor the unit closely. When power reaches the outdoor unit, it should not show the EE error anymore. Also, keep an eye on LED 1 and LED 4 on the board, because if these aren't working, that could indicate another issue. Since it's hot today, the system has a delay setting of a few minutes. Some inverters power on very quickly, but this unit takes its time to initialize properly. Now the outdoor unit has received power, and both LED 1 and LED 4 are working. LED 4 is steady, and LED 1 is blinking, which is the correct behavior. The main issue we were addressing was the EE error, and as you can see, no error is showing on the display now. I also heard the switching sound from the outdoor unit, which comes from the AC fan relay, confirming that it is engaging correctly. The system is now trying to start the compressor, which means the PCB is fully functional. Once I attach the compressor and other components, everything should run smoothly. Click on the left or right thumbnail to watch our next videos, and subscribe. Thank you.